Imagine an invisible wall in the sky. This is the sound barrier, a limit imposed by the very air we breathe. Sound travels as waves, compressing and expanding air molecules. At sea level, these waves propagate at roughly 767 miles per hour. As an object approaches this speed, sound waves bunch up in front of it. This creates a pressure wall, a formidable obstacle for any aircraft daring to break through. Breaking this barrier is no small feat. It requires immense power, precise aerodynamics, and materials that can withstand extreme forces. The first successful supersonic flight in 1947 marked a pivotal moment in aviation history. The quest to conquer the sound barrier has led to countless innovations that have benefited aviation and other fields. Designing an aircraft capable of exceeding the speed of sound presents unique engineering challenges. Aerodynamic efficiency is paramount, as drag increases dramatically at supersonic speeds. To combat this, supersonic jets feature sleek, streamlined designs with sharp swept-back wings. The shape of the nose cone is crucial for reducing drag and managing shockwaves. A sharp pointed nose cone helps to pierce the air, creating a more gradual pressure increase and reducing wave drag. The fuselage too is carefully sculpted to minimize drag and maintain stability at supersonic speeds. Power is another critical factor in supersonic flight. Jet engines, specifically turbojet and turbofan engines, provide the necessary thrust to overcome the sound barrier. These engines compress incoming air, mix it with fuel, and ignite the mixture to produce powerful exhaust gases. Maintaining control at supersonic speeds requires advanced flight control systems. The extreme conditions of supersonic flight demand materials that can withstand intense heat, pressure, and aerodynamic forces. Aluminum, a staple in aircraft construction, is insufficient for supersonic applications. Instead, engineers turn to advanced materials like titanium alloys, composites, and even specialized ceramics to meet the demands of supersonic flight. Titanium, known for its strength-to-weight ratio and high melting point, became the material of choice for many supersonic aircraft components. Its ability to withstand the extreme temperatures generated by air friction at supersonic speeds made it ideal for use in the aircraft's skin, structural components, and engine parts. Composite materials, combining different materials to achieve superior properties, also played a crucial role in supersonic aircraft design. Carbon fiber composites, known for their exceptional strength and light weight, found applications in wings, tail sections, and other structural components. These materials offered a significant weight advantage over traditional metals, improving fuel efficiency and performance. Breaking the sound barrier comes with a price: the sonic boom. As an aircraft surpasses the speed of sound, it creates a shock wave, similar to the bow wave of a boat. This shock wave propagates outward and downward, reaching the ground as a loud, startling boom. The intensity of the boom depends on the aircraft's size, altitude, and atmospheric conditions. Imagine a sudden clap of thunder, startling those on the ground below. That's the sonic boom, a phenomenon inseparable from supersonic flight. It occurs because the aircraft, traveling faster than the speed of sound, compresses the air in front of it, creating a cone-shaped shockwave. This shockwave carries a significant amount of energy, which is released as a loud boom upon reaching the ground. The sonic boom is not a single event, but rather a continuous effect as long as the aircraft maintains supersonic speed. The need to mitigate the sonic boom has been a driving force for research into quieter supersonic technologies. Section 5: Concorde, the rise and fall of supersonic travel's icon. The Concorde, a technological marvel of its time, remains synonymous with supersonic travel. This sleek delta-winged aircraft, a joint venture between Britain and France, captured the world's imagination when it entered commercial service in 1976. For over 2 decades, it transported passengers across the Atlantic at twice the speed of sound, shrinking travel times and redefining luxury air travel. Imagine crossing the Atlantic Ocean in just over 3 hours, sipping champagne at twice the speed of sound. That was the allure of the Concorde, an aircraft that pushed the boundaries of aviation technology and captured the spirit of an era. The Concorde's reign as the queen of the skies was not without its challenges. The sonic boom limited its operational routes primarily to transatlantic flights over water. Its high operating costs and limited passenger capacity made it a niche market, accessible only to the elite few. The tragic crash of Air France Flight 4590 in 2000, while not directly attributed to its supersonic design, cast a shadow over its safety record. Section 6: Boom, Supersonic, a new era of high-speed flight. The dream of supersonic travel didn't die with the Concorde. Companies like Boom Supersonic are developing new generations of supersonic aircraft, aiming to make high-speed flight more accessible and commercially viable. Boom's Overture, a sleek 88-passenger aircraft designed to cruise at Mach 1.7, promises to connect cities across the globe in half the time. Imagine a world where a business trip from New York to London could be completed in under 4 hours. That's the vision driving Boom Supersonic and its ambitious Overture project. Boom's approach focuses on several key areas: reducing the sonic boom, improving fuel efficiency, and utilizing sustainable aviation fuels. The Overture's design incorporates technologies aimed at mitigating the sonic boom's impact on the ground, potentially paving the way for supersonic flight over land. The success of Boom, Supersonic and other ventures hinges on overcoming the challenges that plague the Concorde: high development and operating costs, regulatory hurdles, and public acceptance of supersonic flight. Section 7. Environmental concerns. Navigating the noise footprint. The allure of supersonic travel must be balanced against its environmental impact. Sonic booms, while a significant concern, are not the only environmental challenge posed by supersonic aircraft. These aircraft consume significantly more fuel than their subsonic counterparts, resulting in higher greenhouse gas emissions. The noise generated during takeoff and landing also poses a concern for communities near airports. Addressing these environmental concerns is crucial for the sustainable development of supersonic aviation. Researchers are exploring various technologies and operational procedures to mitigate the environmental footprint of supersonic flight. These efforts include designing quieter engines, optimizing flight paths to minimize noise exposure, and developing sustainable aviation fuels to reduce carbon emissions. By altering the aircraft's shape and employing innovative technologies like quiet boom designs, engineers aim to soften the sonic boom's impact, making it more akin to a distant rumble than a startling clap of thunder. These advancements could potentially pave the way for supersonic flight over land without causing excessive noise disturbance. Section 8. Technological advancements, shaping the future of supersonic jets. The quest for faster, quieter, and more efficient supersonic aircraft drives continuous technological innovation. Researchers and engineers are exploring cutting-edge concepts and technologies to overcome the limitations of current supersonic flight. These advancements span various disciplines from aerodynamics and materials science to propulsion systems and noise reduction techniques. One area of active research focuses on supersonic laminar flow control. This technology aims to maintain smooth airflow over the aircraft's surface, reducing drag and improving fuel efficiency. By delaying the transition from laminar, or smooth, to turbulent, or chaotic airflow, engineers can significantly reduce drag, leading to substantial fuel savings. Another promising avenue involves advanced propulsion systems. Researchers are exploring concepts like scramjets, which are supersonic combustion ramjets that operate efficiently at hypersonic speeds, which is Mach 5 and above. Section 9. Economic viability, the high cost of breaking the sound barrier. While technological advancements continue to push the boundaries of supersonic flight, economic viability remains a significant hurdle. Developing, building, and operating supersonic aircraft is an expensive endeavor. The high costs associated with research and development, specialized materials, and complex manufacturing processes contribute to the hefty price tag. The Concorde's economic struggles highlight the challenges of making supersonic travel commercially viable. Its high operating costs, limited passenger capacity, and restrictions on supersonic flight over land contributed to its financial woes. To achieve commercial success, future supersonic aircraft must overcome these economic barriers. One approach to improving economic viability is to target a niche market. By focusing on business travelers and high-net-worth individuals willing to pay a premium for speed and convenience, supersonic airlines could potentially operate profitably. Section 10. The future of supersonic travel, a balancing act. The future of supersonic travel hinges on striking a delicate balance between technological innovation, environmental sustainability, and economic viability. Overcoming the technical challenges associated with supersonic flight, such as reducing the sonic boom and improving fuel efficiency, is essential for gaining public acceptance and regulatory approval. Environmental concerns must be addressed head-on. Reducing noise pollution, minimizing greenhouse gas emissions, and mitigating the impact on the ozone layer are crucial for ensuring the sustainability of supersonic aviation. Adopting sustainable practices such as using sustainable aviation fuels and optimizing flight paths will play a key role in mitigating the environmental impact. Economic viability remains a significant hurdle. Reducing development and operating costs, exploring new business models, and potentially targeting a niche market are crucial for making supersonic travel commercially successful. Section 11. Conclusion. Pushing the boundaries of speed and innovation. The quest to break the sound barrier and conquer supersonic flight exemplifies humanity's relentless pursuit of pushing boundaries. From the Concorde's iconic delta wings to the sleek designs of future supersonic jets, the journey has been marked by technological marvels and unwavering determination. While challenges remain, the allure of high-speed travel continues to drive innovation. As we venture further into the 21st century, the dream of supersonic travel is being reimagined. New technologies, sustainable practices, and a focus on economic viability offer hope for a future where supersonic flight is no longer a luxury reserved for the elite few, but a viable mode of transportation for many. The sound barrier, once an insurmountable obstacle, now represents a testament to human ingenuity and a stepping stone to even greater achievements. The pursuit of supersonic flight is about more than just speed. It's about pushing the boundaries of what's possible.